Hello. So we are back. This is, I think, part 4 of our video series for creating agentic RAG applications using LandGraph and with an OpenSearch backend. Today, what we're going to do is to start to do a first run after I've made some homework following the previous session. And on the first run, we're going to probably see some issues or some stuff that we want to fix, and then we can tackle that. So without further ado, let's switch to actually looking at the code. As a reminder, we are building an agentic RAG application that can answer any Elasticsearch, OpenSearch, or ClickHouse question. And in order to do that, we are basically running on top of the documentation. So we pulled a lot of documentation content, and we're running on top of that. I have OpenSearch already running. There you go. So I have OpenSearch running. It's running on Docker. It's here under Docker Compose. So a pretty simple Docker Compose environment. And I've ingested the data already that we did on the previous chapters. We built the ingestion. Pretty simplistic at this point. And the index mapping is now fixed. So we basically have only the interesting fields ingested, and it's all there. As a reminder, we have on the agent code base, we have this graph that looks like this. So essentially, we validate the question, we generate keywords potentially, we retrieve the data, and then we generate the response. And as part of that, we basically, and one second, and so we have the app running already, and it's pretty easy to, give me one second. Okay, so it's pretty easy to basically run this now. We can basically do something like run a very simple question. I did some tests before we just started. So obviously empty questions are going to be pushed back by the fast API models. And now I can ask some stupid question like, what is the time now? And the validate node essentially is going to push back. I'm sorry, I can only answer questions about Elasticsearch, OpenSearch, or ClickHouse. So that's like very basic stuff. And obviously we want a very stupid or very simple model, very cheap model to do this validation. So we can actually not pay a lot of money for those kind of validations. And then I also added, in addition to the answer, I also added the ability to get back the sources for anything that has been used in the answer. So if I'm going to do a different question now, I'm going to ask it, how to create a new index in Elasticsearch. It's going to take it a little bit longer. So it goes through the validate step, generates tokens, basically the keywords, which we can look at what it does. It should basically be pretty simple. Then retrieves the data, retrieves the document, and then generates it back as a response. And then indeed we get a response based on the provided documentation, which is something we probably want to remove from the generation. Here's how to create a new index in Elasticsearch, and then it kind of details everything in a Markdown format. And in the end, we have the sources. So we can actually see that we got enable and auto indices, which is, I don't know even if it's from Elasticsearch or not. And then rollover, update mapping API, examples, create index from source API, index creates index from source. So this looks like pretty much the only relevant document at this point. And then other stuff like contact connectors, which is something around the Elastic security solution, index rollover and routing allocation in Elasticsearch, also not relevant. Index lifecycle management rollover, again, not very relevant. So basically, because we do keyword search, every time the keywords that we have, which is, let's assume those are the keywords, how to create new index in Elasticsearch, then those documents will be pulled into context, and then the model will generate. Now, I think the answer we got is pretty good, right? So in order to create an index, you need to use the create index API. The most direct method is to use it this way, and then you have a link to documentation, and then even a console example. But A, we use too many tokens. B, we kind of direct the conversation with irrelevant documentation that is being provided into the context. And third, maybe we have some mistakes here, right? So maybe we have this kind of knowledge-based article from, I don't know, ClickHouse maybe, and then it gets pulled into that. So we need to kind of filter and find a better way of doing that. So this is one thing we want to do. Another thing I want to do is to look at the generate keywords method. I want to make sure that I understand what it does. Let's close this one. So the generate keywords is doing something pretty smart in this sense. So, and we probably want to output that, right? So it doesn't take the actual text that we have. So how to create an index in new index in Elasticsearch. It actually generates the keyword. So you run a search query planner for a documentation knowledge base covering Elasticsearch and the Elastic Stack, OpenSearch, and ClickHouse. Given a user question, generate between 1 and 5 set of keywords that will help find the relevant documentation. Each keyword set should target a different angle or aspect of the question. Each keyword in a set can be one or more words. Now, this works, right? So this basically makes sure that even if I write something like something completely awkward, like let's try to bypass those kind of things, right? How to generate an IDX, right? So let's kind of make sure that we completely go astray and can completely use keywords that do not exist. I expect this, the generate keywords thing, to be able to generate those keywords, but that got blocked by the validation endpoint, which makes sense, right? But if I'm going to do how to generate an index IDX in Elasticsearch, takes it a few seconds, and then I'm guessing it will generate the right question. So based on the provided documentation, I cannot find specific information about generating an IDX, but documentation covers, and those are the documents that it pulled, right? So we have in the sources, range field types, keyword type. So it wasn't able to generate it. So what we want to do, we want to output the keywords that it has generated. It's probably being pulled into the context, right? So keywords, if we go to the application itself, agent app, this is the create app, models, this is the response routes. So we have the query response, AI invoke question, and then it generates the source documents. The response is a query response. So we can go in here and do, so those are the sources, and let's add keywords, which is list of strings. Let's use this notation, and basically we are going to return this always, field description keywords used for lookup. So there's better ways to visualize the flowings within LangGraph. We'll cover that later on, but for now I'm just using it this way. So I want to see that in the response, and then here I need to basically do something like keywords, and then I need to access the state. So result dot sources. It's probably somewhere here. I don't have that to complete, so I'll add that later. But the idea is that within, I want to return the keywords themselves. This is the doc path for each doc in result get document. So it should be something like result dot probably keywords. We can quickly check that. Keywords. I think it's running over here. It should have restarted automatically, just delay it on the safe side. Let's run this. I'm expecting to get back, in addition to the sources, I'm expecting to get back the responses. So we have validation errors. Input should be a valid dictionary. So it's a dictionary. I'll change that after, but the idea is that once I can see the keywords, I can go in and debug that. What we are missing more than just this debug information is this ability to basically understand the flow and also to be able to remove documents that are not from the sources, that are not really interesting for us, right? So basically, if the graph is going to do this basic validation, generating the keywords, then retrieving the documents, between the retrieval and the generation step, we have to make sure that there's a couple of ways of doing that, right? But we have to make sure that we don't put documents that are completely irrelevant. So one additional thing that I would want to do is to either remove the documents completely, so kind of do a quick check per document to make sure if it's relevant or not, or within the generate step to make sure that we kind of tell it, ignore irrelevant information that does not correspond with the question. And then one additional thing that we can do, we can kind of categorize the documents, right? So on the generate keywords, instead of just generating the keywords, we can generate some structured query plan, if you will, which would contain the set of keywords to run. As a reminder, this is in nodes. So the response here is just a set of strings. So keywords, a list of strings. What we can do is to ask it to generate, let's say, a JSON response. And in that JSON response, other than the set of keywords, we can generate a list of, there's also some filters. So for example, we can say, this is a query about Elasticsearch because we kind of identified that one way or another, and then we can apply some additional filter. Now, what's important to remember is that the retrieve step at this point is only going to use keyword matching, and I guess this is where it fails. Again, we need to see the actual keywords, but I guess this is where it fails, because if the documents that we look for have those keywords, then it will actually match it. So let's assume the request is for create index Elasticsearch. So the document title or the document contents have to contain those exact words. Once it has a different spelling, for example, creating a new index instead of create new index, if we didn't use stemming, which could or could not be a default in our index, then it would fail to load it up. So the most relevant document is not going to even appear there. And then again, if I'm using a different verb instead of create, like generate or initialize or something like that, then it will definitely fail. The way to fix that is to move away from just keyword search and then add semantic search. So we use the vectors to do that. And that's the big topic that I wanted to discuss today. So what we want to do is we want to update this retrieval step to be semantic aware, or to be more of a semantic, not just keyword search application. And then the way that it's going to do that is we're going to encode the data, the texts of the inputs, and then also of the searches to vectors, and then use vectors to do it. We still want to use the keyword search because of various reasons. For example, if you're looking for a name of a person or a name of a location or something like that, it's not necessarily going to be vectorized correctly. And also, you always want to prioritize higher the exact matches. So we're going to do that. But in order to do it, we want to discuss vector search and what it means. So in order to do that, I've prepared some materials that we can go over. And then in the next session, we're going to actually see that in action. So the basics is that what we've done now is basic keyword search. And that's what we often use to doing in many cases and in many search systems that we have. So there's like basic normalization, like in English, removing stop words, or sometimes, and definitely lowercasing, obviously removing punctuation marks and so on. And then the actual scoring is using algorithms like TF-IDF and today mostly BM25 to be able to find the more interesting, the more relevant documents. It's very, very fast, that we know, but we just saw, and there's plenty of other examples where and how it actually fails in real life. It is not able to find semantic meanings, right? And then we also have some scoring challenges. For example, if that specific word appears more than once, then a specific document will rank higher. Sometimes it's good, sometimes it's not. But since in our use case, we ask an LLM to generate the keywords for us, so we ask it to understand the query and generate those keywords for us, then it's not necessarily going to match on specific keywords, and we do need to use semantic understanding of the query. To be honest, any keyword search engine that is going to rely completely and entirely and solely on keyword search is probably going to fail in the AI or agentic era, because we are going to rely more and more on LLMs to generate searches for us. And we see this all the time. So when you go to ChatGPT, you go to Claude Code, anytime they do web search, they kind of understand what they need to search, and then they make up the search terms. It will often be similar to what you would look for, but sometimes it will actually be different. And we need to take that into account. And that's exactly what we have seen here. So essentially, what we need to do now is we need to encode the text that we have, the sources, the documents that we have, using vectors. And then we're also going to use the query. We're going to embed the query using the same embedding model. Sometimes there are going to be some differentiations. And then execute that as a semantic search with Elasticsearch or OpenSearch, which is what we use at this point. So the vector database that we have in the backend. This search is going to be executed with what we often call ANN or KNN or approximate KNN. And the idea is that a vector will represent the text and the meaning, and any vector that is in some proximity to it will actually be a good match. The closer that is going to be to our query vector, the better the match is. And obviously, we need to only pick the closest vectors, but we also need to understand what is the what is the gap, what is the difference, and then find some cutoff point as well. We're going to discuss two different types of vectors: sparse vectors and dense vectors. Sparse vectors are usually just vectors that have a lot of zeros in them, and each position in the vector, each coordinate, will essentially be an indication of a specific word, whether it has appeared and how many times or anything like that. And then they're called sparse because there are going to be so many zeros over there. So it could be a vector with 30,000 coordinates values, but most of them are going to be zeros. So we are only going to have like a couple of dozens, maybe hundreds of values in the vector itself. Dense vectors, on the other hand, are not going to be zeros. They're going to be dense, and they are often costlier to generate or to compute using LLMs or other models. But they're going to be dense, but sometimes they're also going to be smaller, and they are going to capture the semantic meaning much better than sparse vectors usually. So a good example for a sparse vector is TF-IDF. So this is what I just mentioned a second ago. Every time you do a keyword search, effectively you're doing some sort of a vector search of sparse vectors, because what we're building is some sort of an array of the values or words that you have in the actual text with some weight, right? And this is the weight is usually either binary, exists or doesn't, or some sort of a TF-IDF value, which means this is the term frequency in the document, and I'm going to give it higher value if it's also kind of rare. So the document frequency, it's kind of rare in the general document space that I have. A more advanced algorithm is BM25, which basically does that, but with some additional nice additions on top of it. It's pretty much the industry standard, and it's something that we consider today as a much better approach or much better variant of the general TF-IDF. So this is a sparse vector. What it captures well is any word that exists, yes or no, and then what document is more relevant to the text that we're searching for, based on how frequent or how unique the words that we're searching on actually is. What it doesn't capture is any semantic meaning whatsoever. So, for example, learn and teach are not going to match at all, because completely different words, even though they have semantically close meaning. There are some sparse vectors that are generated through some models that are still able to capture some semantic meaning one way or another. And as an example, we have Splade. So Splade would take a text like affordable electric cars, which using the standard way keyword search are not going to be matched based on those terms, because if I wrote cheap, I didn't write affordable in the document, then the query is not going to find it. But Splade is able to do it, because it is able to basically generate a sparse vector that would also include the word cheap and maybe some notion of the word price with different scores into that. And then even though some terms are not in the original text, it's still going to be found and scored based on that. So any search for affordable is going to find it, as well as electric car, and car and vehicle, and so on. And maybe the electric car will also map to Tesla and other vendors, and so on. So Splade will actually be able to do it. It's still a sparse vector, so it's still relatively cheap and fast to compute, but it's going to capture semantics, but it's not going to be as costly as dense vectors, at least to compute. And when we talk about dense vectors, essentially we talk about LLMs or other types of very large models that would be able to generate a list of a vector, a list of numbers that will represent the meaning of the document, of the text. Now, every dense vector model, like Cohere Embed version 4, which we absolutely love, OpenAI has good embedding models, AWS Titan, and so on. There's also open source ones, quite a few, including from Snowflake, from Microsoft, from Alibaba, and many more. And anytime you run those, they basically run a very large compute, GPU bound. The open weight open source models will sometimes be, they will have some cheaper or smaller models that you can run also on more commodity hardware. And then we'll generate those values. I'll show you in a second how it looks like. And those values essentially are going to be representing the meaning of the document. Now they're going to have a limit of the number of tokens or the size of the text that you can push into them. So you cannot just push a document with 1 million words and expect to get a vector that is representative. There is going to be some limit, usually in the hundreds of tokens, sometimes more. But it also makes sense for you to not push so much of a large context, because if you have a document of, let's say, 20,000 words, like a book or something, every chapter, maybe every page, maybe every bunch of paragraphs is going to have a different meaning. They're going to talk about something else. So it doesn't make sense to create a vector out of the entire thing. You want to have a vector that is going to look at a chunk of the text that you have over there. And that's where we're going to discuss, not now, but in the near future, some chunking strategy. So if we have a piece of documentation or a piece of knowledge-based article that talks about a specific topic, and that article has become big or touches on multiple points, we definitely want to make sure that that specific article is split to several chunks, and each chunk is going to contain one discussion item or one micro topic, and then that topic is going to be encoded into a vector. And then when we search for it, we actually find the right chunk, the right chapter, the right bunch of paragraphs, and so on. And that's particularly important with dense vectors. So that's the chunking strategies that we're going to look at. And again, this is also something we haven't done just yet. Something else that is interesting and important to think about is a technique called HIDE, which is hypothetical document embeddings. And that goes in the length of, instead of thinking of keywords that I might want to search for, because I know that the document that I have are going to be concentrating on documentation, on guidance, or answering some question. So if a user of mine is asking me a question, maybe instead of taking the keywords and executing them as a search, or taking the expanding the question a bit more, maybe I need to hypothetically generate an answer, even if it's not the right one, but then it should contain the context in which the responding, or the ultimate answering response is going to contain the same words or the same context, or essentially the same vector. So I'm going to generate, using an LLM, I'm going to generate this kind of hypothetical response. It could be correct or not. We don't care. We're going to generate a vector out of that, and then this vector is what we're going to use for the question. So we can generate either a vector from the question or the set of keywords that we have used an LLM to generate, and hopefully that would work, or we can generate a potential response and embed that. Now, whether to go one route or the other is really dependent on the data set, on the types of questions you're going to expect, and this is essentially what we're going to do in the next chapters of the video. So before we wrap this up, I just want to also highlight two additional things. So one, anything that we do from now on, and we'll attack that in the next couple of chapters, we're going to start looking at precision and recall. We're going to start discussing which method is going to be better for what we're trying to do. And in order to measure that, we're going to look at two metrics. One is precision, how many documents from the documents that I found are actually relevant. And the other one is recall, how many relevant documents I should have found, but I haven't. So looking at the example that we just had, so we have this, and essentially, so if I ask this question, like how to create an index in Elasticsearch, and then those are the sources that we got, and essentially we got a snippet of enable auto indices, rollover, ILM rollover, which are not relevant, this is a low precision document. So out of the 5 or 10 documents that we got, only one I think was relevant, which is create index from source API. So our precision is pretty low. I would also assume there is some very good documents that we haven't found. Like I'm assuming there is a documentation piece that's called create index API, Elasticsearch creating an index, something like that. It's probably there. We can go in and look for that. And then because we haven't found it, or any document that we haven't found will essentially be lowering our recall. So I'm assuming the recall here is not great either. So what we want to do in order to understand which method we want to try is to start measuring precision and recall. Measuring precision is usually easier. Measuring recall is a little bit harder, but we will discuss that following up. And then other than measuring precision and recall, in the end, like I said, the keywords that I use do have some meaning. So it's not just the semantic meaning of what I'm interested in is going to be interesting and the one that I want to use. I want to make sure that I'm also combining the keywords and then basically taking the vector search, the semantic search, combining it with the keywords to boost some very specific documents or documents that are more relevant maybe to what I'm searching up. Then I'm going, like I said, maybe we want to filter out some documents in one way or another to sharpen the message or the response. And then we're going to use some methods. RF is one of them, and we'll discuss that in more length, is to basically combine them in a smart way to make sure that if one method was significantly better than the other, so we are actually going to use it correctly. So in the next session, next even 2-3 sessions, what I'm going to do is I'm going to one, improve everything that we have going on right now. So basically, I want to have visibility, not just for the sources that we used for generation. I want to understand the keywords that we generated. I want to introduce some level of, we call that evaluation. I want to make sure that we evaluate, we automatically or manually signal what results we liked, what results we didn't, and then find ways to tune based on that. The more requests, the more examples, data set that we have is going to be more helpful for us. And then maybe we want to start eliminating some content that is not relevant, or grade some and kind of boost them up even further. Following on that, we're going to add some more complex approaches, because once we know how to measure, once we know how to evaluate, then we can figure out what works and what doesn't, and then quickly iterate from that. So far, I think good progress. In just very few hours, we were able to generate some very basic chatbot on documentation, which is nice, but it's still far from being perfect. And what we're going to do in the next few chapters is to iterate and improve on that. Any questions, any specific requests, feel free to pop up message, and I'll definitely be love to take them on. See you in the next chapters, and thank you for tuning in.